The European Space Agency Euclid telescope just delivered one of the biggest hauls in recent astronomy. 31 newly confirmed quasars from the very early universe. Published this month in the journal Astronomy and Astrophysics. That number alone roughly doubles the total known sample of quasars this old in a single announcement. 2 of them are now the most distant, and therefore oldest, quasars ever directly observed, dating to when the universe was only about 670 million years old. Just 5% of its current age of 13.8 billion years. Their light has been traveling toward us for roughly 13 billion years before Euclid's instruments finally caught it. Each one is powered by a black hole weighing in at around 1 billion times the mass of our Sun. That number is the part astronomers are still trying to explain. Let us sort the signal from the noise. Before the mystery, the basics. A quasar is not a star. It is the blazing core of a young, active galaxy, powered by a supermassive black hole at its center pulling in enormous amounts of surrounding gas and dust as that material spirals inward. Friction heats it to extreme temperatures, and the resulting glow can outshine every star in the galaxy around it combined. Bright enough to be visible across billions of light-years of space. Because quasars are so luminous, they act as a kind of cosmic beacon, letting astronomers detect and study galaxies from eras far too faint and distant to observe any other way. Euclid, launched specifically to map the shape and structure of the universe using an unusually wide field of view, was not originally built as a quasar hunting mission. But its combination of wide sky coverage and sharp resolution turned out to be exactly the right tool for spotting these exceedingly rare, faint, ancient light sources that easily get lost among ordinary foreground stars. Get a sense of the actual numbers involved. These 31 quasars sit at what astronomers call redshift 6.6 to 7.8. A way of measuring how much the expansion of the universe has stretched their light on its journey to us, and therefore how long ago that light left its source. The 2 record holders, catalogued as EUCLJ 172902 and EUCLJ 125308, emitted their light when the universe was roughly 670 million years old. For comparison, that is like looking at a baby photo of the universe taken when it was about 5% of its current age. Each of these ancient quasars is powered by a black hole already weighing approximately 1 billion solar masses, according to the research team, including ISA fellow Antonio Lamarca, who noted this result more than doubles the number of known quasars from this specific, extremely early era. Finding even one this old and this bright is difficult. Finding 31 in a single survey is a genuinely large statistical jump. Here is why astronomers care beyond the impressive numbers. Standard models of black hole growth assume they start small, from the collapsed remains of massive stars, and grow gradually over hundreds of millions or billions of years by consuming surrounding matter. A black hole weighing a billion suns, existing when the universe was only 670 million years old, is a serious timing problem for that standard picture. There may simply not have been enough time for gradual growth to produce something that massive, that early. This is part of a broader puzzle astronomers have been wrestling with for several years now. Sometimes nicknamed the problem of impossibly early black holes. And it has led to competing theories. Perhaps some early black holes formed from unusually large collapsing gas clouds rather than dying stars. Or perhaps growth in the extremely dense early universe happened faster than current models assume. Having 31 fresh data points instead of a handful gives researchers a genuinely larger sample to actually test these competing ideas against. Here is the part that deserves real caution. Distances and ages this extreme are not measured with a tape measure. They are inferred from redshift calculations and modeling assumptions about how light stretches across an expanding universe. Assumptions that are well established but still carry margins of error, especially for the faintest, most distant objects where signal is weak and easily confused with foreground contamination. The paper itself describes these as newly confirmed candidates from a specific survey field, meaning follow-up observations with other telescopes will likely refine, and could occasionally revise, some of these classifications and precise ages. A sample of 31, while a major jump from before, is also still a small number in strict statistical terms when trying to draw firm conclusions about how typical or unusual these black holes actually are across the entire early universe. And the impossibly early black hole puzzle remains genuinely unsolved. This discovery adds data toward answering it. It does not settle which competing formation theory is correct. Quick recap. Euclid identified 31 ancient quasars, roughly doubling the known sample from the universe's first billion years, with 2 dating back to when the cosmos was just 670 million years old in each. Powered by a billion solar mass black hole. A finding published this month in Astronomy and Astrophysics. So, signal or noise? Signal. This is a peer-reviewed result from one of the world's major space telescopes, using well-established redshift methods. And it genuinely and substantially expands the known sample of extremely early quasars. Some noise risk shows up only if you treat this as solving the impossibly early black hole mystery. It does not. It sharpens the puzzle and gives scientists more data to test their competing theories against. Which is exactly how good science is supposed to work. The honest takeaway. A real, well-documented discovery that raises better questions rather than delivering a final answer. Subscribe for the space stories that separate an actual discovery from a headline reach. Signal from the noise. Every week.